Welcome to the lesson video on support vector machines. In this video, we're going to talk about support vector machines, which are one of the most accurate, most flexible methods for classification, particularly when the separation between classes is nonlinear. So let's start off this video with a toy example. We have two classes here, red and blue, and clearly linear separation is not appropriate. There's no linear separator between these two classes, and it just doesn't make sense. The geometry is wrong. But it's not hard to imagine drawing a circle that's going to separate these classes. It's fairly clear that the circle is going to separate these two classes just fine. In fact, this circle could be thought as in the similar way we talked about maximum margins. Using sort of circle geometry, we could take the innermost circle and outermost circle and define a margin between those. That would give us some separation in a maximum margin classifier or soft margins type of way of thinking. But it's in a circle geometry, it's using different functions than linear functions. So we're looking for separation in the direction of this function, little f. And we would separate by if the f is bigger than k, you're in the blue class, and f is less than k, you're in the red class. And so this example is a good example that motivates how we think of support vector machines. We're going to do things like a support vector classifier with soft margins, but we're not going to use linear geometry. We're going to use some higher dimensional geometry, some geometry that comes from adding functions to the data, applying functions to the data that allow us to do our margins in some other, turns out, in a higher dimensional space. And so we'll talk about how that works in a bit. So let's summarize what we're going to talk about, support vector machines. What we do with a support vector machine is we use a function to put the data in a higher dimensional space and then use support vector classifier in that higher dimensional space. So why would we do this? This allows nonlinear classification, just like we saw in the toy example a moment ago, but with advantages of soft margins. Right? And there's really nice math using kernels that handle this mapping into higher dimensions. So it's taken care of. It's not computationally expensive unless you have a lot of data points, and it's something that works real well, fairly robustly if you pick the right kernel. So that's an important if. You also have to have numerical data for the support vector classifier to work in its natural setting. Okay, so let's talk a little detail. So on the left-hand side, I have this toy data set that we looked at a moment ago, and now we're going to think about it in this terms of mapping this data to a higher dimensional space. So on the left-hand side, we have this data in the xy plane. On the right-hand side, we have x and y. We've added a dimension z. And so here's our dimension z. And we're working with z equals x squared plus y squared. So that takes the plane, and it maps the plane into this parabola, this paraboloid shape here, and then it comes up in the front and the back, and so it's a bowl shape. And so what we have here are the parabolas along the x-axis and along the y-axis that kind of help us imagine this bowl shape. Now, if we take our data, each data point on the left-hand side as an x and a y coordinate, we add the z coordinate, that's approximately where our data is going to sit. It's going to sit on this two-dimensional bowl-shaped surface in 3 dimensions. Once we have this data like this in 3 dimensions, separating with a linear separation surface is possible. And so that somewhere around where I've shown this, above the red class and below the blue, maybe halfway in between, is a separating hyperplane. And in fact, we can estimate that using the soft margins in a support vector classifier way. And so here's the dotted lines that show approximately where the margins would be. All the red classes are on this surface below the lower dotted circle, and the blue class is above the blue dotted circle. So we take our original data on the left-hand side, we map it to the right-hand side to 3 dimensions. We can separate with that separating hyperplane. Then we look at what's called the pre-image of that separating hyperplane, or where it crosses that bowl back in the original data space. And that tells us where our separating curve is in the original space. And so that's a really good picture of support vector machines. The only thing we have to talk about is how do we pick this function z, and how does the kernel method, or the kernel trick is what it's called, allow us to do this computationally relatively efficiently? And I say relatively efficiently because it's really a giant computation that's turned into a feasible but still large computation, depending on how many data points you have. And so we'll talk about that a little bit. And so here's sort of the recipe. This is kind of a high-level recipe. Again, to implement this in a software is a non-trivial task. This process came from computer science, and it's a beautiful math, but we're not going to get too far down into the weeds in it. And so this statement, 9.18 from the Introduction to Statistical Learning with R textbook. And so this first statement is about the linear support vector classifier. So that's the linear classifier, not support vector machines yet. And it can be represented by this function. And this is the function that gives us f. And f, remember, is the function that assigns our outputs based on the input parameters. And so you take an input x, and then you take its inner product with every xi in the data set. You multiply those by some alpha I parameter, and then you add beta naught to that, and that would give you your estimated output for regression in this setting. Okay, so if the linear support vector classifier can be represented this way, we're taking that as an if, we're not showing it can be, but this formula would give you the linear support vector classifier, then you have to estimate these alpha i's, where there's one alpha I for each training example, and that gives us n parameters. There's n training observations. And so the second paragraph helps us explain how you would train this, how you would determine those alpha i's. And to train those, this is an important thing. All you need are the inner products between all pairs of training observations. And so in some sense, this is built on looking at the distance between all pairs of training observations using distance computed using this inner product. Well, we can take this whole framework, and instead of using the inner product there, we can replace that by what's called a kernel. And so it's a way of measuring distance between 2 points, between x, our new observation, and each xi in our training set. And so we can use what's called the linear kernel, which is the linear support vector classifier. We can use a polynomial kernel of degree k. So all we're doing is replacing this function inside here with one of these functions here. So it's a polynomial kernel of degree k, or what's called a radial kernel. And this is a common kernel to use. It's also called a radial basis function. You'll notice here there's a parameter gamma, and that tells us how, so this is an exponential. Let's think about this function a little bit. You have an exponential of this piece here, which is the distance between the 2 points squared. So this is going to give you some sort of bell-shaped curve, and this gamma tells you how quickly that bell-shaped curve drops off. So let's look at the outputs from support vector machines on a couple of different of these kernels. This is a good description, but to get a good feel for how it's working, it's better to take a look at the output and the separation surfaces and the classification regions. So this is a data set that you've been used in our interactives. And on the right-hand side, we have the decision boundaries. This is Fisher's iris data, so it's measurement from a bunch of iris plants, 3 different species. And we're only using the first 2 features. So this is the sepal width, and sepal is part of the plant, and the sepal height. And so what we're getting here over on the left-hand side, these are all our different possible kernels. And on the right-hand side, you can see the classification or separation boundaries between the different classes. And so here we have on the top in blue, we're showing our training data. In green, we're showing 10 times cross-validation. And on the red, we're showing the results of the test data. And of course, we really just care about the cross-validation because that's going to be the robust measurement of our accuracy. And so when we use a linear, which is what we're looking at right now, a linear separation kernel, we get the results we see on the right, and our cross-validation result is 0.2733. We use a second degree polynomial. You'll notice these decision surfaces now look a little bit like parabolas, slightly. They're very close to linear, which suggests that second degree isn't really needed. And you'll notice our cross-validation value hasn't changed at all. So in this case, we don't need this more complicated type of separation. Linear would have been sufficient. Third degree polynomial, you'll notice we have increased flexibility in our decision surfaces, maybe they're third degree polynomial type curves, and a slight increase in our error rate or slightly worse performance. It's not statistically significant in the change, but we're taking a more complicated method using third degree polynomial here and getting results that are not significantly better. So we wouldn't use this. This would be not worth using. Now we use the fourth degree polynomial. And at this point, I could see an argument here that maybe there's some sort of shape in here that this is doing that's useful, but certainly I don't know why the blue should really extend all the way up through there. That's a little odd. Our cross-validation error has gone down to 0.255. I don't really think what we have here is a better classifier than the linear, even though our cross-validation error rate's gone down a little bit. I would choose the linear. I imagine that would be more robust than the fourth degree polynomial curve. And then we have radial basis function, which again is giving us sort of odd shapes. And there's this red region down here, which looks a little strange. And our cross-validation error has gone up, so things have gotten worse. And then sigmoid, which we don't have a plot for here, but lots of error for the sigmoid kernel. So out of these kernels, we would pick the linear kernel. And what we're doing here is typically how you pick your kernel. You look at the different kernels, you look at the scatter plots and decision surfaces, if that's possible, to the extent that that's available. If I'm looking at 50-dimensional space, this might be hard to do, meaning 50 feature variables. But to the extent you can look at the scatter plots and decisions, you would consider that, and you would look at your cross-validation error rate for a number of different kernels. And so in this case, I'd pick the linear because it has an error rate that's among the lowest, and being a simpler type of decision surface, it's going to give me something that I would think would be more robust. Now let's look at the nonlinear data. So here's data that's synthetically generated from a couple of random distributions, random Gaussian normal distributions. And you look at our linear kernel, and it's not doing a very good job, right? It is called the nonlinear data because you can't separate these two classes with a line, with any sort of linear separation surface. So our error rate here is 0.2985. So 30% of our data is being classified wrong. And so that's not particularly good. Second degree polynomial, slight decrease in error, but still not very good. Third degree polynomial error, we actually seem to be following a trend. If you look at the data in this shape, particularly through here, we seem to be following some sort of separation area, and we can see a sort of associated drop in our cross-validation error rates down to 0.2. So if I had to choose a linear kernel, then this would seem to be a reasonable choice. We jump up to fourth degree, allows further flexibility, and it doesn't really seem to be doing a particularly good job, and our error rates gone up. So I wouldn't use this. The radial basis function seems to be doing a pretty darn bang-up job here. Our error rate is down to about 4%. So we went from about 30% down to about 4% by picking the right kernel in this case. And if you look at the separation curves on the right-hand side, those are really good separation curves. I don't think I could draw something by hand that would necessarily separate those two classes better. So in this case, the radial basis function seems to be doing a good job. And then the sigmoid isn't really doing a good job here. The sigmoid gives you a classification result that's similar to logistic regression. Not exactly clearly, but there are similarities. It's using the logistic regression sigmoid function as your kernel. Okay, so now what we have is we're going back to the radial basis function, but what we're plotting here is not the decision boundaries themselves, but the probabilities that are associated with those decision boundaries. And so the reason I want to look at this plot is it really gives us a nice sense of how the support vector machine is seeing these two classes. And it's a beautiful picture. It really is. The support vector machine learns these separations. We're going to talk in a moment about ROC curves on the heart data. And so when we talk about ROC curves, really what we're talking about is a detection problem where one class is your target class and the other is your non-target class. And so if we think about the heart attack data, which we'll look at in just a second, what we care about is our target class. We want to detect people who are going to have heart problems or have heart problems that haven't manifested yet. And so the target class are heart problems. The non-target class is everybody else. And so what we often do is we look at some parameter to separate those out, like a probability that you're going to have a heart attack. And so what we do is we look at different values of how our classification results are working based on different values for that threshold or for that probability. So for this picture we're looking at, if the blue were my target class, and I said, I want a probability 90%, give me threshold at 90% probability. So this would be only the things that I'm really certain are blue. So that would be something like this maybe. Everything inside that curve is the data points that are a probability of 90% or greater, or probability of 0.9 or greater of being in the blue class. So if I wanted to say, not just separate green from blue, but tell me the ones that I'm really sure are blue, I would use a threshold not of 50%, which is what, when we did the classification result screen a moment ago, it's somewhere in there. That's the 50% separation curve. Everything above it is probably green, better than 50-50 chance. Everything below it, probability better than 50-50 that it's a blue. And maybe I want to be certain that I'm getting everything that's blue. So maybe I want to set a probability of, say, 0.25 that you're blue. And so that would give me a separation curve, something like this maybe. Everything inside this region is a probability of 0.8 or greater of being green, thinking green my background class, and then a probability of 0.2 or greater of being blue. So that would give me, in the region outside that, would give me, I would be certain to get all the blues, and I might get some green as well within that threshold. And so this is the type of things we think about when we're doing ROC curves. We've talked about these before. We set different thresholds on our probability and look at two different rates. The true positive rate, which is the fraction of your target class observation scoring above the threshold, and a false positive rate, which is the fraction of the non-target class scoring above the threshold. Here we're looking at the heart data. And so true positive rate, so you're setting a threshold on your probability, and your probability is a probability of having a heart attack. Your true positive rate is the fraction of actual people who had a heart attack that would have scored above that probability. False positive are the people who would not have a heart attack that scored above that probability. And so you can compute true positive rate and false positive rate for any probability. Those two rates for a probability are the fraction of, if blue is our target class, the true positive rate would be the fraction of points that are blue that are inside the area set by the threshold, and the false positive rate would be the fraction of green points that would be inside of there. So if we set a high probability, like this region I keep tracing, then we would get not all the blue points, maybe say half the blue points, so our true positive rate would be 0.5, but our false positive rate would be 0 because there are no green points inside of here. And so ROC curves allows us, as we've talked about before, to get this trade-off between true positive rates and false positive rates. And so what we do is we plot the true positive rate and false positive rate as a function of the probability as these curves. And so we have one curve for support vector classifier and one curve for LVA on the heart data. And so down here at 0, for both of these, we have a very low probability, right? At 0, your probability is 0. So you have 0 true positives, but you also have 0 false positives. As you increase your probability, you move along this line, and then maybe probability of 0.5 is somewhere up here where you're getting a lot of your actual heart attack cases would be detected because they would be above that probability, and you have some moderate number of false positives down here. So like let's pick a different color for a point right here. I'm detecting 85% of my heart attacks, say, and 15% of people who aren't going to have a heart attack would get flagged. So if I set my probability for heart attack here, I could detect 85% of the heart attacks before they occur, but I'm going to accidentally suggest a possible heart attack in the future for 15% of people that aren't going to have a heart attack. So that might be an okay place to set your threshold. And you pick a trade-off between how much you want to catch everybody. So for heart attacks, since it's a really bad thing, I might want to pick my threshold up here where I'm going to catch 95% of the heart attacks, but I have, say, a false positive rate or a false alarm rate of 35%. So 35% of the people who come into the doctor and are measured with the measurements in the heart data, and then they put through a classifier and their probability comes out to whatever that is or above, 35% of the people are going to be flagged as you're a heart attack risk. But out of the people who are going to have heart attacks, 95% of them are going to be flagged as high risk before they have their heart attack. And so things can be taken to take further tests or to start remedying conditions that are putting them in that very high risk category. So those are how ROC curves are used to estimate picking a threshold based on the trade-offs in the sort of practical situation where things are used. There's one more thing here while we're talking about ROC curves. AUC is called area under the curve. It's a way to estimate. If you look at these two curves, sometimes the blue seems to be better than the red because it has a higher true positive rate at the same false alarm rate. And sometimes the red is above the blue, which is telling us the red has a higher true positive rate for the same false alarm rate. So to get a measure of overall performance, what is often used is called the area under the curve, or the AUC, and it's exactly the formula is in the name. It's just the area under each of those ROC curves. That it gives us a broad estimate overall of the ROC curve, of how well this is performing. And just one final note on ROC curves: they're only used when you have a two-class problem, and particularly when you have one class that's your target class, and then everything else is your background class. So here's support vector machines, and we're comparing those versus linear discriminant analysis and support vector classifier. On the heart data, the top part is performance on our training data. And you can see here the support vector classifier and LDA are both doing reasonably well. Support vector classifier is a linear classifier, so it's about as good as LDA in this situation, which is not a giant surprise because it's a linear classifier. Over here, in red, we have our support vector classifier compared to the support vector machines, and we see the support vector machine with this gamma. Remember, gamma is it's a parameter in your radial basis function kernel that seems to be performing the best. So up here on our training data, our best performing algorithm is support vector machine with a gamma being 10 to the negative 1. When we apply this to our test data, however, we don't see a big increase. So this improvement works on our training data, but not our test data. So we seem to be overtraining to our training data. In particular, the difference between LDA and support vector classifier is not significant. And then this difference between support vector classifier and our support vector machines is not different. So what we've seen here in this example, the support vector machine doesn't give us a big advantage over LDA because probably the data has a reasonable linear separation, and adding the nonlinearity with the support vector machine doesn't give us a bonus. But we saw when our nonlinear data, the support vector machine got us a high increase in performance. We went from 30% error rate to 4%. And so in that case, it's the nonlinear nature of the data and the need for that nonlinear separation that support vector machine was able to provide. So review, and I love to have a picture that reminds me of how something works, and this picture on the right-hand side tells you how really well support vector machine can work when your separation is nonlinear. So what is support vector machine? It's a classifier where we use a function to put the data in higher dimensional space and then use a support vector classifier in the higher dimensional space to get our separation. Why do we do this? It allows nonlinear classification with the advantage of soft margins. There's really nice math using those kernels that handles the mapping in high dimensions. And it's one of the most accurate classifiers if the data is continuous numerical data and the right kernel is used. Thank you very much for watching.